This is video 3 for the invisible light unit. Let's take an overview of the electromagnetic spectrum. So what we have here is we have radio waves all the way up to gamma. And we can see that it goes radio waves, microwaves, infrared, visible light, ultraviolet, X-ray, gamma. So to get us started, we're going to start talking about AM radio. This is what you would consider like an ordinary radio. Not many people mess around with this, but every car tends to have an AM side. They got AM and FM. AM has a wavelength of around 300 meters and a frequency of around 1 megahertz. So AM, because it has such a high or such a long wavelength, it can bend around a lot of things. So AM usually tends to be kind of your long range radio signals. Then for TV and FM radio, we have a slightly higher frequency. And remember, since we have a higher frequency, then we can have more information. So this one goes all the way down to 3 meters, and it has a frequency of around 100 megahertz. And that should kind of make sense. You know, if we're decreasing the wavelength by a factor of 100, we should be increasing the frequency by a factor of 100. And since the frequency goes up, information theory tells us that higher frequency signals can carry more information because they can switch back and forth faster. So this is a frequency high enough to allow high information things like TV. Microwaves. We use this for radar, ovens, and cell phones. This has a wavelength of around 10 centimeters and a frequency of around 3 gigahertz. Now mega is million, giga is billion. Now we come to infrared, and we kind of have a couple ways of thinking about infrared. First one is heat infrared. So we're talking about, like, you know, the heat produced by a human or a heat lamp. This wavelength is around 20 micrometers. So micro is 10 to the negative 6, so that's a millionth of a meter. The frequency is around 15,000 gigahertz. Next we have near infrared. Again, it's kind of a warming kind of effect. It's a little closer to visible light. This is a lot of the light from the sun. So this has a wavelength of around 1 micrometer. And the frequency is going to be about 3 times 10 to the 14th hertz. So remember, 10 to the 14th, that's where we're starting to get into visible light. Speaking of which, visible light, it's the stuff we can see. We can use the acronym ROY-G BIV to help us remember the different colors. About a half a micrometer. And it's in the neighborhood of 6 times 10 to the 14th hertz. Now we come to ultraviolet. This is what causes sunburn, skin cancer. Has a wavelength of around 3.3 micrometers. So notice there's not a whole lot of difference between the near infrared and ultraviolet. The frequency is about 10 to the 15th. All right, X-ray. This is the stuff that can pass through water but not bone. And again, we're going to see a bit of a jump here, 10 to the negative ninth meters. That would be like, let's see, it goes milli, micro, and then pico. So this would be like a picometer. And then the frequency, again, we see a bit of a jump, be about 3 times 10 to the 17th hertz. And finally, we finish up with gamma rays. This definitely can cause cancer. Gamma rays also account for a lot of the cosmic radiation that hits the Earth. 10 to the negative 11th meters is for the wavelength. And then a very high frequency of 10 to the 19th. So for radio waves, again, we kind of have like two different classifications if you want to think about it that way. We got AM and FM. These are electromagnetic waves at frequencies between thousands of hertz to tens of millions of hertz. Not tens of thousands, tens of millions. Sorry about that. And, you know, there's not too many bits per second. The frequency is just not high enough to support a lot of information to be traveled through there. But it's enough for audio and TV. We just got to make sure we use higher frequency radio waves for the TV. So, you know, radio wave is perfect for, you know, sending music to your cars. It's great for sending, you know, like those, like the hobbyists with the ham radios and things like that. Okay, so microwaves then. These are actually a lot like radio waves, but much shorter wavelengths. So just like with radio waves, they pass through clouds and smoke, so they are very reliable, and we use them for radio waves, ovens, and cell phones. Now let's talk about radar. This is a method for emitting radio waves, primarily in the microwave band, into the sky and looking for reflections off of metal objects, such as airplanes. And then from the time it takes a signal to come back, we can then calculate the distance that plane is from like the station that was sending out the waves. So microwaves are used for radio because of the short wavelength. So that means that they don't spread too much from a smaller antenna. You can aim them more accurately and determine the direction of a plane. So it's also important, though, that for this application, that the travel be uh, pretty that it travels pretty easily through clouds and smoke. I mean, we want radar to work even on rainy days. Um, for microwaves, and it's kind of funny how this was found out. There's an individual who found some soldiers standing in front of a microwave antenna on a cold winter night and asked them why are they standing there, and turns out it's because, well, it's warmer if we stand here. Um, we now understand that microwaves absorb, or the microwaves themselves are absorbed by water molecules, and then that energy is converted into heat. So what microwaves do is it gets the water molecule to start oscillating back and forth, or up and down, if you will. So see how this molecule is being flipped upside down. So we're getting it to kind of rotate, if you will. And what the microwave does is it causes it to rotate, and it actually goes into resonance. It's resonating with the frequency of the microwave. And if you remember, temperature is a measurement of the average kinetic energy, and kinetic energy depends on the speed of an object. So basically what the microwave does is it gets these water molecules rotating, and the quicker we can get them to rotate, the faster they're moving, so the higher their kinetic energy, and the higher the kinetic energy means that, well, there's more temperature, the higher the temperature. And that's basically how microwaves work. So when those soldiers were standing in front of that dish, they were just getting their water molecules to start spinning faster. The power is low enough that they didn't get cooked, though. Now, mirrors reflect waves. So think about your bathroom mirror. It's reflecting the visible light waves hitting it. Whenever the space between particles is shorter than the wavelength of the wave, those particles act like a mirror. So microwaves have a wavelength of around 3 centimeters. So when looking at the wire mesh on the door of a microwave, notice that mesh, since the space between the wires on the mesh is less than 3 centimeters, that mesh acts as a mirror to reflect the microwaves and keep them trapped in the oven. And this is true for all kinds of waves. So if you want to think about your bathroom mirror, the space between the particles in the bathroom mirror must be smaller than the wavelength of visible light. And that's what it allows it to act as a wave. Going on the other end of the spectrum, X-rays and gamma rays, these are very high frequency, very, very high frequency, very, very short wavelengths. But they're still light. They're just light we can't see. So X-rays are emitted by rapidly accelerating electrons. So the X-ray machine that your dentist uses, it makes a beam of electrons and shoots them at a tiny piece of heavy metal, like tungsten. When the electrons suddenly stop, because the tungsten stops the electrons, they emit X-rays in the same direction that the electrons had previously been moving. So that's how X-rays are produced in medical offices. Gamma rays, they are emitted when a nucleus is going through radioactive decay, and basically it's moving particles again. It's just that instead of moving electrons, we're moving like the protons inside the nucleus. Again, the wavelength is going to be extremely short. The frequency is going to be very, very high. So every wave packet of X-ray and gamma ray, it contains substantial amounts of energy. All right, we're going to finish up the video here. The fourth video, we're going to talk about some different medical imaging technologies.